Any questions? Okay. We're doing momentum stuff. All right, so just put up symbols on the board. What does that mean? Or what does,
Impulse.
all right, the,
Changing the method.
okay, which is,
Impulse.
okay. What letter did I use for impulse? Did I? I. Okay. So besides finding change in momentum, finding the impulse through the change in momentum, what's the other way that we can find it?
Like the equation for impulse?
Right?
Like the equation for impulse?
Yes. Oh, let me
Force,
follow up.
force multiplied by changing time.
Yeah, force times time. So if you're ever asked to find impulse of something, you can find it either way. If you have mass and velocities, you can find it from change in momentum, or you can find it from the force and times change in time. What I'm gonna do is I'm gonna take the beginning and end of this, since they're equal to each other. And I'm gonna divide by time. So we end up with the force by itself is equal to the change in momentum over the change in time. Change in momentum, or what formula for momentum?
MV.
So we have the change in mass times velocity over change in time. If the mass is constant, it won't change, so I can just factor that out. So this becomes m times the change in velocity over the change in time. And what's the change in velocity over change in time?
Acceleration.
So this expression right here is just Newton's second law, because we got force is equal to mass times acceleration. Questions up to here before I make it more complicated? Let's make it more complicated. Instead of having to wait below my comfort level there, let's do it over here. Suppose the mass is not constant. What object, man-made object I'm thinking of, is it designed for the mass not to stay constant?
When something stuck to something and becomes something else, like
Okay, you can still treat that as still two separate masses that happen to have the same velocity. But yeah, that would be an example of what I've asked. It might evolve into a read my mind exercise. Rockets. Why does the mass not stay constant for rockets?
Because they drop parts as they,
Oh, even without dropping?
oh, because they burn fuel?
Yeah, they're burning fuel. So fuel's getting ejected out the back, so the rocket's basically, or gas inside the rocket is forcing the fuel out the back. By Newton's third law, the fuel must be pushing back on the rocket, and that's what gets the rocket to go. But mass is not constant for a rocket. So what happens to that? I got this change, I have my force is equal to the change in momentum. That's still true. That's equal to mass times velocity over change in time. But if I've got mass is changing, I can't just factor it out. How would you deal with that? And probably product rule. There's only one person in here who had calculus. I'm guessing only one. Okay. Mainly, I asked the question just to see if anybody happened to know it. But why this works this way beyond the scope of the class, so you just have to just trust me. Basically, it's the velocity times the change in mass over change in time plus mass times the change in velocity over change in time. You do each part separately. So you assume velocity is constant and do change in mass, and then you assume mass is constant and do change in velocity. This is slightly more formal. We still have our mass times acceleration here, but we got this extra term, which is related to what's called thrust. But this, where I'm heading on this, that is the more generalized form of Newton's second law. Because if you've watched the kinetic energy video, the one formula that you must know, because that kinetic energy formula stays true. Newton's second law, was incredible for his time, but we became more sophisticated and realized there is a more generalized form. So this is just basically a more general Newton's second law. That's more of a side note, a longer side note, but let's just run through a quick problem here using impulse. A rock. Let's give it a mass here. 3 kilogram rock falls from 20 meters to the ground. To the flat ground. It makes a dent in the ground. To me, hole implies much deeper than what I'm going for here. And it was stopped. In 0.01 seconds. What was the average force applied to the rock to stop it? feet was the dent. So this problem's gonna bring in a lot of little bits and pieces we've done from a number of chapters up to now. All right, questions about reading my handwriting? All right, so first bit, I need to know how fast that thing's going just before it touches the ground. In other words, in a 20-meter fall, how fast is it going? We got two big approaches on that one. We could use the chapter 3 stuff, or we could use the chapter 7. Chapter 3 or chapter 7? Let's do them both. What the heck? Chapter 3. Oh, I did not state. Starting at rest. All right, so I have a rock that starts at rest and I drop it. Chapter 3, there's an equation that Hewitt uses. I'm going to put it into slightly different language. Displacement is equal to 1/2 AT squared. That's if an object is starting at rest and then has constant acceleration. That's the formula for displacement versus acceleration in time. So let's figure out how much time it takes to fall. So what's the displacement as it falls? Okay. So what did you just do just then? What has now been established?
The displacement.
Pardon?
The displacement?
More than that. That is the displacement.
The height where
Say it again.
like the height where the rock falls.
No, that was given in the problem. We're establishing a convention here.
Alright.
The height given in the problem.
That up is a positive direction.
If up's a positive direction,
Oh.
that's not what was established here. What was established here? You're on the right track.
Down is positive.
Yeah. So by saying 20 here, that immediately makes down positive. That's equal to 1/2 times, what value do we use for acceleration?
9.8
Give me the whole thing.
meters per second.
There we go. Times t squared. So the math problem is 20 is equal to, well, 1/2 times 9.8 is 4.9. That's the math problem. So how do we solve for t?
For
Sorry, louder?
Divide by 4.9.
That's right. We have to get down to the heart of what we want is t, so we gotta get rid of all the other stuff first. So first we get rid of that thing, that pesky thing up front. And so t squared is equal to whatever 20 divided by 4.9 is,
4.082.
4.82.
4.082.
0.082. And now to solve for time, and then, so if we square root both sides,
2.020.
is that right? I think, okay. And units? Thank you. We're not at the end of the problem, so I didn't have to put units in there. That was just sort of a fun little addition there. There's no doubt you were thinking. Then we have to figure out how fast it was going just before it hits the ground. Well, Hewitt's got another equation for that. If it starts at rest, which it does, so So if I just drop an object, that's how fast it's going. Or you could look at it this way, the velocity is changing 9.8 meters per second. So every second it's changing by 9.8 meters per second. So you just multiply the two. So it's going 9.8 meters per second squared times 2.020 seconds.
19.796. Meters per second.
Yes.
Sorry, it took me a second.
Presumably the pause was to let someone else have a chance if they wanted it. Sure. All right. So we have how fast it's going just before it touches the ground. Questions up to here before we do a chapter 7 approach? All right, let's see. I want some space. We'll do it up there. As it's falling, tell me all the forces acting on it while it falls.
Wait.
And is that a conservative force or a non-conservative force?
Conservative force.
Absolutely. So energy is conserved. So my energy at the beginning is equal to the energy at the end. I got two types. I got kinetic and potential. You know the question's coming up. If you need to look it up in the little bit of time you have, please do. Ready? What's the formula for kinetic energy?
1/2 mv squared.
I like the strong voice right there. It'd be nice if others had joined in on the course. Now let's do it again. What's the formula for kinetic energy?
1/2 mv squared.
Thank you for now. What's the formula for potential energy?
Mass times height times gravitational acceleration.
Answered the wrong question. That's answered my next question.
Oh.
Which one?
Yes, there we go. Say it again, Marina.
Which one?
Yes, the one associated with weight.
Okay.
Now,
Mass times gravitational acceleration times height.
okay, so we got mgh, the initial, is equal to the same stuff except final. 1/2 mv final squared plus mgh final. Presumably readable by, I guess, Jennifer, you're the farthest away. Is that readable?
Okay.
That was okay. Is any of this stuff equal to 0? Or, better wording, which of these are equal to 0?
The initial velocity.
Yes, this is speed. It's still 0. No vector symbols.
Oh.
That's 0 because it starts at rest and all right, anything else equal to 0?
Our final potential is equal to 0 because our height is 0 because we're stopping at the ground.
Oh, that's not y. Oh, okay, or y is the height 0 at the end.
Because it hits the ground.
Oh, that's not y. I'll accept that this is 0. Not because it's the ground, it's because of something else.
The gravitational acceleration.
No. In some ways, it's a much more powerful reason, and in some ways, it's a much simpler reason.
Would it be because the initial
not for that reason. Think about potential energy. Remember, the formula actually has a plus some constant. We got some flexibility here. What matters is the change, not the actual value itself. It's 0 because Ty said so. You establish where h is equal to 0 wherever you want. I could have made h is equal to 0 at the top. And then the height of the end is negative 20. But we establish where we want 0 to be, and then everything else is based on that. All the other potential energies are based on that. So this is because Ty said so. More powerful than because it's the ground, and much simpler. All right. So we're now left with this. Bring that equation back up again. So I have mgh initial is equal to 1/2 mv final squared, that's a v. So we start out with all this potential energy and no kinetic,